So the general multiplication rule, so that's everything we just went over, all in textbook jargon, I guess. Probability of A times probability of B given A. I'll reinforce that as we go forward because it's notation that's very easy to lose sight of. And also, sometimes it's kind of hard to identify what the condition is within a problem. Sometimes it flat out says it, but then sometimes it's buried in the context. And so you have to kind of mine through the wording of a question to figure out what is it really asking for, And so, but this is a good concept, the complement rule, because this is a nice little shortcut. And we kind of touched on it a little bit with that textbook problem, but this is something that that's going to kind of formally address it. It says the probability of at least one is equal to 1 minus the probability of none. And I'll just give you a quick look at that theoretically. So if we look at, and I'm kind of stealing my own thunder here a little bit, a probability distribution, which is a set of x values and the probabilities of those x values occurring. Just make a little table. All right, so x represents success. And then P of x represents the probability of success. This is going to be under the complements and conditional probability stuff. So I'll highlight it for you. It is, where's my highlighter? This rule. 27. All right. So, success, I'll say success is. So, because it's really the number of successes, the amount of successes, the quantity of successes, a variety of different ways you could say it. But if you just say successes, you get the job done there. I don't need too much because I'm going to just take advantage of the last bit of ice I have here. So let's say you're dealing with a situation where you have the possibility of having no success, 1, 2, or 3 successes. All right, a fictitious situation. X. And let's say your probability of having no success is 0.5. Your probability of having 1 success is 0.2. Probability of having 2 successes is 0.1. And probability of having 3 successes is 0.2. All right. So it really doesn't matter what the circumstance is. You could kind of create your own backstory. You're salvaging underwater. You're a scuba diver. Like you went down 3 times and you salvaged nothing. You salvaged one piece of equipment that's valuable once, like out of the 3 attempts. Twice or all 3 times you came up with something that was valuable. Whatever backstory you want, right? But what this idea is saying is that we could do a couple of things. We could find the probability of getting 0, and that's 0.5, or we could find the probability of getting at least 1. Now, there's a couple of ways that we could get the probability of at least 1. One way is easier than the other. In this case, it's a small table, so actually neither way is difficult. But conceptually, one way is going to be easier than the other. Right? At least 1 means 1 or more. So here's at least 1. So one way I could find the probability of at least one would be to add up the 0.2, 0.1, and 0.2 again. All right, in which case I get 0.5, and that'd be perfectly okay. All right. The other way to do it would be to take the probability of getting none. So here's none. And subtract that from 1. So I could say 1 minus the probability of getting none, which is 0.5. And the result would be equal to 0.5. All right, so either way, you're going to get 0.5. Right? So you're going to do it one of two ways. You're either going to identify the none situation and subtract it from 1, or you're going to add up your values that fall into the at least one category, which is everything but the none. So it's a question of what's going to be easier to do. Depends on the number of successes that you could have, right? So this diver only went down 3 times, but what if they went down 300 times? All right? To add up 300 probabilities, that would not be fun. To take one probability and subtract it from 1, I wouldn't call that fun, but I would say that's pretty easy. All right? So that's really what this is coming down to. It's a nice little nifty shortcut for figuring out the probability of having success in any capacity. All right? Because what this is showing, I mean, and you never know, because depending on the situation, maybe one success is all you need. Right? I could think of plenty of situations at a casino where one success is all you need. You know, you're betting, like let's say you got $3,000, and you're going to bet on 3 spins of the wheel. You're going to bet $1,000 on each spin, and you're going to put it down on a single number, which is paying out at 35 to 1, which means any one of those bets is going to yield you $35,000 in winnings. All right. Do you need to win all 3 of them in order to feel happy? No. Any one of them will do the job. I mean, you'll feel really happy if you win all 3 of them, $105,000. All right. But actually more than that if you let it ride. I mean, that's nerve-wracking though. But any one of them and you're going to feel pretty good. All right. So getting at least one win at a 50% clip, not too bad, you know. But it's also showing that you could bust. You could lose $3,000 at a 50% clip. You know, based on these numbers, which I just made up off the top of my head, so they're not even remotely related to casinos. So I don't want you walking out of the room being like, all right, going to Atlantic City, I got a 50-50 chance of winning $35,000 after 3 spins of the wheel. It's not going to play out that way, I promise you. But yeah, like, I would rather have that information going into a situation. You know, what are my chances of going bust after, and, you know, dial it down. You know, let's say a $10 bet on 100 spins of the wheel. Yeah. Or even simpler, $10 bet on 35 spins of the wheel. You know, because if you win, so 35 spins of the wheel, if you win, you're going to win $350. If you lose every single time, you'll lose $350. All you need to do is win once to win $350 out of 35 spins of the wheel. Now, there's a 1 in 38 chance that that's going to happen, so it's still not guaranteed, but when you put it in that context, now it's like, wait a minute, I got a puncher's chance here. You know, I can play, you know, like you go to Atlantic City, if you're anything like me, you go there with a budget, you lose the money, that's the money that you brought to play with. That's your entertainment money for the evening or the weekend. Once you lose that money, you don't go to the ATM, you don't keep putting yourself in more debt. That's it. You know, like I'm done. That was my gambling money. Now I'm done. All right? But if you could stretch that money out, you're stretching out your entertainment. Now, if you could figure out a way to make it last for 35 spins of the wheel, that's a fairly lengthy period of time, right? All you need to do is win once or twice, and now you've extended the amount of time that you can play. Now, if you hit a few times in a row because you found one of those dealers that can hit their spot, now maybe you make some money, right? So you're kind of riding the wave until maybe you hit the spike, and then pull your money out and go have some fun, you know? So these kind of concepts can help you make informed decisions about stuff like that. Because what I've noticed, because I'm not, I promise you, I mean, I sound like it probably, but I'm not a big gambler. Last time I went to Atlantic City was like 2 years ago. The last time before that was, oh Lord, I don't even know. But I know enough about it. So when I was there last, you know, I'd use my strategies, my math strategies, and I would see people, they'd come up to the table and they'd be like, all right, $1,500 on black. They'd either win or lose. They win, they acted like they were some like prognosticator that had some kind of inside knowledge. I'm like, no, you just got lucky. You go to the next table, you're going to lose it all, so enjoy that. And then somebody comes over, does the same thing, and they lose, and they're shocked. Oh man, how did that happen? I'm like, well, it's gambling. They call it that, you know. So the reality is, it's gambling, and you don't know what you're doing. So here we are, you know. These kind of things can help you make an informed decision. If you're of age and you have any intention of participating, I mean, I keep saying Atlantic City, but you can go closer places now. If you have any intention of doing that, I recommend that you, like when you're driving, like be a passenger in the car. Have somebody drive for you, because nobody can ever find the time to do the probabilities at home, like at work. You know, you're sitting around having dinner. Oh, let me bust out the calculator and do those probabilities. But for whatever reason, it always occurs to people when they're on their way to the place. You know what? That crap he was talking about in class, I better get on that. I'm about to gamble. And then you're sitting there driving by, you're driving the car, like, I can't do it now. Take the wheel. You know, I gotta crunch some numbers. So maybe that's you, you know. And we'll explore roulette in more detail down the line. But definitely worth it. Okay. Find the probability of tossing at least one head in 2 tosses of a fair coin. So with all that stuff in mind, it's pretty straightforward, because I'm just going to set up my notation: probability of at least one head Now, we do have to keep in mind how many trials are happening, because it doesn't really make its way into the formula, but it does make its way into the concept. So that's going to be 1 minus the probability of no heads. Which in turn, because it's 2 tosses of a coin, it's 1 minus the probability of getting a tails and a tails. I'm writing a lot more than you'd probably write on a test, only because, again, it's note-taking. 1 minus the probability of getting tails and tails again. I don't have to worry about the conditional, that vertical line thingy, because we're looking at independent events. All right. One of the tricky things about multiplication rule is identifying when events are dependent or independent. Sometimes it's obvious, sometimes it's not. Basically, the idea is if the probability would remain unchanged depending on any things that occurred prior. Like if I was going to wear shorts no matter what Alexis said, then it's independent events. Here it's independent events because there's 2 sides of a coin no matter how many times I flip it. One side's going to be tails. All right?
So 3 of them are independent events, or just the last one? The last one?
The tails and the tails. Yep. So we're looking at 1 minus probability of tails is 1/2 times 1/2. So 1 minus 1/4 is going to be 3/4. All right. Now, you can see numbers 2 and 3 are the same setup. If anybody's looking for typo bonus, we don't need as much space for numbers 2 and 3. So you could submit that. Because it's really just kind of an extension. Because it would be the exact same setup. Except I would say 1 minus the probability of tails and tails and tails. All right, because it's 3 tosses of a fair coin. So 1 minus, well, let me show the intermediate step. 1 minus the probability of tails times the probability of tails times the probability of tails. So instead of multiplying 1/2 by itself, we're going to do it by itself 3 times. Question?
How did you get number 3 over 4? I understand 2 times 2 is 4, but how did you get?
Well, 1/2 times 1/2 is a quarter.
I'm sorry?
1/2 times 1/2 is a quarter. So 1/4, and so 1 minus 1/4. Also something you typed in the calculator. Yeah. So same idea here. 1 minus 1/2 times 1/2 times 1/2. You just pop that in your calculator. And that's why I'm just kind of glossing over that, because you just type it in exactly how you see it. 1 minus 1/2. You could use the fraction function or not. It doesn't make a difference.
Do you use parentheses in that?
If you're not using the fraction function, then you have to then you'd want to use parentheses, yeah. But if you are using the fraction function, then you don't need them. So we get 7/8. Now, numbers 1 and 2 fall in the category of types of questions that you could probably do a different way. Like if I listed out all the different ways in which you could get 2 tosses of a fair coin. So I could do a tree diagram, I could list out the sample space. I just count them up. Same idea with number 2, there's only 8 outcomes. Number 3, you got 37 tosses of a fair coin. That's a lot. So it's going to be way more than 8 possible outcomes. But we have a recipe here. Because looking at what we did in numbers 2 and 3, you could see really it's just the same structure, but we're just going to have a differing amount of 1/2. Here I had 2 1/2. In number 2 I had 3 1/2 for 3 tosses of a fair coin. So how many 1/2 am I going to have in number 3? I think I heard it. I had 2 1/2 in number 1. I had 3 1/2 in number 2. How many 1/2 am I going to have in number 3? 37. So it's going to be like, whoa, I'm not writing all that out. So instead, I'll write it as 1 minus 1/2, and I'll raise it to the 37th power. Wasn't necessary for the previous question, or 2, because writing 1/2 times 1/2 times 1/2 wasn't terrible. But writing 1/2 times 1/2 times 1/2 times 1/2 all the way up to 37 1/2, that's brutal. I don't want to do that. At least not today.
So would you write 1 minus PT to 37 if you...
Yeah, exactly. So 1 minus 1/2. A little caret symbol. We haven't really, I mean, I've used it a little bit, but I don't think I've explained it enough. Power of 2 is this symbol here generally, right next to the comma. If you want to raise it to any other power, it's the caret symbol. Automatically creates a power field. And then we would go to the 37th. All right, we've done it a little bit, but I kind of hand waved over it, so I figured I'd make sure I at least said it clearly at least once. All right, so it says 1, but it's not really 1, right? Because there is still ways in which you can get all tails. I mean, you flip a coin 37 times, you're not going to get every single outcome to be tails very often. Like if every one of us did that, flipped a coin 37 times, I would be shocked if anybody got tails every single time. So what we're getting here, the calculator is saying 1, but so we'll write the 1, we'll write what the calculator says, but this is saying virtually 1. All right, so virtually is like, I mean, if you put it in normal people speak, it's the same as saying damn near. So it's damn near 1, but it's not exactly 1. It's 0.999999999. I keep throwing in 9s there, but it's so close to 1 that it might as well be 1. All right. So now on a test, am I going to ask you to write virtually 1? No. If the calculator says 1, write the number 1. All right. That being said, I'm not going to ask you to go for 37 tosses of a fair coin either. So, you know, the odds of that coming up are remote. Actually, the probability of it coming up is 0 because I'm just not putting that. I'm not putting a question that will have this answer on the test, but the concept will be there. All right? So maybe it'll be at least 1 head in 10 tosses of a fair coin, or 15 or something. Something big, but not that big. But I did want to go over a case where you would get something that was so close to 1 that you would say, well, practically speaking, it's a guarantee, but it's the whole Dumb and Dumber thing. So you're saying there's a chance, you know, like that's really what it is. Like technically speaking, I mean, if I flip a coin 10,000 times, it is mathematically possible that you could get all of those outcomes to be tails. But if it happened, you'd be shocked, all right? So, and that's gonna kind of, I mean, that'll lead us into the second half of the course, where we start talking about how we can take information about probabilities on a small scale and project it out into the larger universe. So it's kind of interesting. All right, so with that being said, I'm going to pop a star on number 4, because it switches up the scenario, but it's the same concept. And we'll take a break, 5 minutes, and then we'll continue with conditional probability.